Hi, everyone. Thanks for joining us at the Protocol Labs Research Seminar Series. Today's speaker is Dr. Gareth Tyson. Dr. Tyson is a senior lecturer at Queen Mary University of London and a fellow at the Alan Turing Institute. He is Deputy Director of the Institute of Applied Data Science, co-leads the Social Data Science Lab, and is Deputy Director of the DAME PhD CDT. His research is in the broad area of internet data science. He's been covered by news outlets such as the MIT Tech Review, the Washington Post, Slashdot, BBC, The Times, Daily Mail, Wired, Science Daily, The Independent, Business Insider, and The Register. He's the author of the paper that he will discuss today, Challenges in the Decentralized Web, the Mastodon Case. The floor is yours.
Cool. Thank you very much for that introduction. In fact, I think you've just taken the first 5 minutes of my presentation away from me, which is always helpful. Cool. So for those of you who haven't met me before, my name's Gareth, and as Jonathan mentioned, I'm a senior lecturer based at Queen Mary University of London. And today I want to talk to you about some of the research that we've been undertaking looking at challenges in the decentralized web. So I'm very well aware that everybody on this call is probably already very much an expert in this topic. So if at any point I'm going too slowly or you just want me to skip certain parts, feel free to shout out, interrupt at any point. I always welcome people interrupting, asking questions and so forth. So before I continue, I should probably also thank Yanis for inviting me to do the talk. Yanis and I, as he said, have been friends and colleagues for quite a while now and been really interested in some of the work that's been going on in Protocol Labs, and been lucky enough to talk to Yanis for quite a bit now about some of the work he's been doing there. So again, at the end, if there's any Q&As, I'm also happy to maybe throw some back at you to understand some of the things that you've been working on as well. Okay, so as Jonathan mentioned, this is a presentation based on a paper that we published about 8 months ago now in the Internet Measurement Conference. And what we tried to do is collect a large data set looking at some of the issues faced within the decentralized. One particular application we had in mind was Mastodon. So we collected a very large data set from Mastodon, and most of the work I'm going to be presenting today is essentially the statistical analysis we did of that data set, looking at how Mastodon works and some of the problems that emerge with the deployment of Mastodon as it currently stands. This is actually a collaborative effort. I can't really take all the credit for this. It was alongside a few co-authors, some of whom you might already know. So let me just turn my laser pointer on and find it. Yeah, hopefully you can see my arrow now. Is that visible, my arrow? Yep. So we have Nishant Sastry, who's a professor now at the University of Surrey. We've got Sagar and Aravind, who are PhD students at King's, and we have Emiliano, who is a professor over at UCL. Now, what I want to talk to you about today is quite simple, and it can be summed up in one straightforward statement, which is it's damn hard to decentralize the web. Now, this is probably something you guys have already come across before, and it's certainly something that many other people have discussed in great detail over the last 200 years. So anybody recognize this chap here? These questions never work very well on a webinar. So for those of you who don't recognize this man, of course, this is Alexis de Tocqueville. And Alexis de Tocqueville was a social historian and philosopher who lived in France about 150 years ago. And he said this, a push towards decentralization in the end actually just became an extension of centralization. Can anybody guess what this may have been referring to? I can give you a hint in advance. It certainly was not the decentralized web. No, of course, it was the French Revolution, a very bloody time in France's history, where the people of France rose up and attempted to decentralize the head of Louis XVI from the rest of his body. Now, initially, this was actually very successful, and it was a rather democratizing movement, but anybody who's read into this at all, or even watched Bill and Ted's Bogus Adventures, will know that very quickly, this decentralization snapped back to a much more centralized version of government, focusing on the personality of Napoleon Bonaparte. And in many ways, this is not entirely dissimilar to what we've seen over the last 25 years of the web. So let's look back to the 1990s and try to understand how the web used to work. It looked very much like this, where you had servers scattered around the world, operated by many different people, running many different websites. And these different servers had their own respective user groups who connected to those servers and used the various, forums, search engines, image sharing services that they had available. Now, in many ways, this was a really cool model. And I probably don't have to sell this to you, but you had a much more symmetrical power structure. You had a very sort of uniform distribution of power across all these different administrators and users. Arguably, it was more resilient because if one of these servers or one of these websites went down, it didn't take the rest of the internet with it. And it didn't have central points of failure. So it's not like you had, for example, individual CDNs operated by individual companies who ran everything. And arguably for privacy, it had superior privacy properties as well, because naturally you didn't have single pools of data owned and operated by individual corporations. No, instead, what you had was data spread very thinly across all of these different services that were not interconnected, they were not independent, and importantly, they were not owned by the same people. Now, if we fast forward 20 years to what we have today, it's a very different picture where we have the web looking like this, where you have a few major players like Facebook and Google who operate these hugely popular global services that nearly everybody in the planet connects to and nearly everybody on the planet is dependent on. Now, easily we could sit here and start bemoaning this model, but actually we also have to acknowledge that there are some benefits to running the web like this. For example, it's really nice that you have this kind of critical mass of users centering on platforms like Facebook. So for example, I could jump on a plane. Well, okay. 6 months ago, I could jump on a plane and go somewhere. And I could likely meet somebody who's on Facebook. I could add them as a friend and we could communicate regardless of where we went in the world. That's a really useful feature. You also have very smart people working for these companies doing orchestrated deployments that mean that in most cases you get extremely reliable services with a lot of innovative services always cropping up to excite and interest users. And one of the reasons this is possible is because, of course, this centralization enables economies of scales where we can aggregate resources and maximize its utility. So I suppose the question that I'm asking today is, if we acknowledge that there are benefits to these two models, can we try to find a way to get the best of both worlds? Now, again, this is not the first time somebody has asked this question. Anybody who's been following British politics over the last few years will know that we're going through a very similar experiment ourselves. And what we've found pretty robustly, actually, is it's incredibly difficult to get the best of both worlds. And half the time when we try to do so, things go terribly wrong. Again, if you pick up a British newspaper, you'll quickly discover this at the moment. So moving back to the decentralized web now, most of you have probably heard of how it works. Of course, you're very familiar with IPFS, but there are inevitably a number of other open source implementations of decentralized models. And the one that we're particularly focusing on today is the Fediverse. So the Fediverse is a sort of model of decentralizing the web in which you have independent servers which federate together to offer common services. And we have all sorts of federated versions of popular platforms that we know and probably love. So for example, there are federated versions of Facebook, there's federated versions of Twitter and YouTube. And the one we're going to focus on today is a federated version of Twitter, which is called Mastodon. Hopefully some of you remember this logo over here, which is the Mastodon logo. So let's just remind ourselves how Mastodon works. And remember, this is one example of the Fediverse. When I describe this, try to bear in mind that most of the other platforms work in a very similar fashion. So for example, you have things like PeerTube, which is a decentralized version of a video sharing platform, and it pretty much works in the same fashion. Okay, so imagine we wanted to set up one of these Mastodon services that offer a micro-blogging platform. What we'd do is we'd buy a server, or we'd maybe hire some VM from Amazon, and onto that we'd install the Mastodon full stack, so the server software. And let's imagine other people in the world are doing the same thing. So maybe Yanis is doing something in Greece and Jonathan's doing something in the US. So we have these 3 different servers with 3 instances of the Mastodon server installed. Now, each one of these is like a mini Twitter, like a little mini Twitter sphere that's completely independent and isolated. And each one of them can start to accumulate users. So for example, I might email some friends or hand out some cards and get people to start signing up to my service. And one by one, they register with the service and they become users on there. And once they're on there, they can obviously start microblogging. So for example, if this user here microblogs, all of the other users who are following him on that server can start to see it. But there's a problem there. So the problem is that what happens if you have users on different servers who also want to communicate to each other? And remember, think back to the example I gave about Facebook when I got on a plane and flew over to San Francisco and I met a friend there. I want to have a model in which I can easily add that person as a friend without having to worry about which server they happen to be registered on. So imagine we have Colin, this is a good colleague and friend of Yanis and I, who is based on this server, which is Jonathan's server. And we have John, who's another friend of ours, who's based on the server that I've set up. So how can these guys now communicate with each other? Well, the way Mastodon enables it is through something called a remote follow operation. And what a remote follow operation does is it tells Colin's server to essentially federate with John's server, such that whenever John creates one of these microblogs, it automatically gets pulled across the internet to Colin's server so that he can see that. And of course, this is happening all the time between all the users on the different servers who want to follow each other. So after a while, what you find is many of these servers now have federated links between them as users follow across the different servers. And this is really cool because, as you can see here, we have a decentralized model in which we have different users associated with independently managed servers, yet virtually they see it as one unified platform in which they can follow each other. So this is a really nice feature of the Fediverse. So at this point, you might say, well, fantastic, great, we've now decentralized the service and we can stop worrying about this. The problem is, there's always this Alexis de Tocqueville coming in from the side saying, actually, no, you've not. What you've built is a decentralized platform, but that doesn't necessarily mean it's deployed and operated in a decentralized fashion. Now, what I want to do for the rest of the presentation now is talk about some of the measurements that we've been doing to try and understand this phenomenon of decentralization and how it works in practice. So we thought about this about 2 years ago, and we started collecting data from Mastodon. And what we did is we started connecting to about 4,000 of their servers. And for the rest of the presentation, I'll refer to these individual servers as instances. And from each of these instances, we gathered the tweets, which Mastodon refers to as toots, from each of their timelines. And alongside this, we also collected the follower graph, so we could see who was following each other. And to understand the infrastructure reliability, every 5 minutes, we started connecting them to test if it was still online. And again, the question that we were trying to answer is, what pressures exist that might be pushing this decentralized architecture back towards a centralized deployment? So what we found was actually fairly positive. So the service was very lively. It was growing, as you can see from this graph, across our measurement period, which was about 18 months. We saw both the number of users and also the number of toots increasing. Now, the number of instances was a little bit stagnant for the first few months, but you also see a growth here, buoyed on by campaigns like Delete Facebook, which some of you may have followed on Twitter. So we were really happy with this because it obviously showed us that people were getting excited about the decentralized web and people were joining and using it. But rather than going through these graphs in a relatively tedious way, what I wanted to do instead is actually go through a thought experiment. And the reason I say a thought experiment is because many of the pressures that exist towards centralization happen because of the decisions made by people like us, the people who set the servers up, or the users who are utilizing those servers. Okay, so let's start off with a simple one. Imagine you're wanting to set up Mastodon. Where are you going to put your server? Where are you going to host it? Well, if you were adhering to the kind of purest form of decentralization, what you do is you'd set up a completely independent network with a completely independent server so that there's no common dependencies between yourself and other servers. How many people actually do this? Well, frankly, it's very few. So what we find is that actually about half of the users are reliant on just 3 networks hosting these instances. And obviously the most prominent one is Amazon. Now, this actually poses a serious question because placing all of our instances on just a small number of well-known infrastructure providers, it's questionable to what extent this is really decentralized. Because if, for example, tomorrow AWS set up a policy that said you can't have any Amazon instances, all of a sudden, what you'd find is about 2/3 of all the content disappears. And that, to me, poses a real threat to the decentralized concept that we're trying to push here. So the next question is, let's flip it and imagine you're a user. If you're a user, which instance would you go to join? Well, of course, as I said before, you have about 4,000 instances to pick from, so there's plenty of choice out there. But what you quickly find is that about 90% of the users join just the top 5% of instances. And those top 5% of instances actually host 95% of the toot content. In other words, the vast majority of users are centralizing on just a small number of popular instances. And this makes perfect sense because if you're a new user coming to join the system, it's unlikely you're going to want to join an instance with just 2 or 3 other users. Instead, you're going to be attracted by those larger instances where there seems to be much more going on. And again, this human desire to go to where the most popular things are really drive this model of centralization where actually a few instances have the majority of power in the network. Now, there are a bunch of reasons why this happens, but this is just one interesting one we found. So this actually shows a breakdown of the number of users, instances, and toots associated with particular topical instances. So for a subset of the instances, they're actually tagged with the type of topic they cover. And what, for example, we see is that Linux is extremely popular in terms of the number of instances. Over half of the instances that we see are tech related. And this again kind of makes sense because, of course, Mastodon is a relatively new project. A lot of people in the tech community are interested in this, and these tech community people set up new instances themed around a topic they like. However, if you start to look at the number of users, you start to see this elephant in the room over here, which is the big red bar. And actually this is related to adult content. So even though over 50% of the instances associated with tech, we find that over 60% of the users are going to instances that host adult content. So again, you see this disparity, but it's still driving the same message home. You've got a small number of users, sorry, a large number of users going to a small number of instances because of these topical interests many people have. So you might be saying at this point, well, okay, that makes sense. We all know how users tick, but at least having this decentralized architecture gives us some degree of reliability, right? Because even though it's virtually centralized, underneath the bonnet, it's actually decentralized with all these servers spread around the world. So we wanted to look at this. So what we did is we started collecting every 5 minutes information about whether or not the server was still alive. And this gave us an idea of how reliable the infrastructure was. And what we found is actually this reliability is rather questionable. So what we found is that about 1/10 of all the instances that we were monitoring were inaccessible for half of the time, half of the duration of our period, of our measurement period. We found those instances offline. Now, a natural conjecture here is, well, probably those instances are just the unpopular ones. So maybe somebody's set up an instance, there's only 10 users on it, they're just doing it as a hobby or they're just doing it as an experiment. So it makes sense that they happen to have a high rate of failure. But actually what we can do is take a look at whether or not this is true. So what we did was we split up the instances based on the number of toots hosted on each one. And you can see this box plot here. So this is obviously those instances that have under 10,000 toots. And these instances over here are those who have over 1 million toots. So unpopular and popular. And actually what we do see is that, of course, the less popular instances do have more downtime. So you can see that the downtime here on median is about 12%. But actually what's really interesting is even these really popular instances, the ones with over 1 million toots, still have these outliers where you have up to 30% of the time we were monitoring them being unavailable. Now this poses, again, big questions, because if we want to make the decentralized web work, we need to make sure that we get sufficient reliability to ensure users don't come in and then soon after leave because they say, well, actually, this isn't as reliable as I'm getting on Twitter. I'm going to migrate back to that particular platform. So in fact, summing this up, what we find is only 5% of the instances have over 99.5% availability. So those ones are doing a great job. And obviously for those users associated with them, they get a very reliable and fantastic service. But for the remaining ones, you might find users disengaging simply because the reliability is not what they're used to on other centralized platforms like Google or Facebook. Now, the next question is, why does this happen? Now, I cannot sum this up in 1 or 2 slides because the reasons are incredibly diverse. And as I said at the beginning, one of the big reasons is that, of course, many people just set these instances up experimentally. So it would be unfair to describe the whole system as unreliable just because a few of those instances are experimentally set up and not maintained. But what we actually also find is that there are some interesting centralized dependencies that we see. So one interesting one is network outages. So as I mentioned before, what we find is that a number of instances are co-located because their users happen to place their servers on the same network. And this happens for a bunch of reasons, but the most obvious one is actually it's quite simple and straightforward to set these instances up on certain networks like AWS, because in many cases, those people have had prior experience with that. So obviously they just go with what they already know. And in many other cases, there are nice, easy to use tutorials online. So for example, if you Google, you can find a really nice and easy tutorial on how to set up Mastodon on AWS. So naturally, if you're a new person wanting to come in and set up your instances, and you Google that, you're going to just go straight and use AWS. Now, what we found is across the duration of our period, we had 6 network outages. So naturally, when those outages happened, we removed all of the servers simultaneously from that network. So these central dependencies clearly do pose a risk to reliability. Another quite interesting one actually was that many of the instances also use the same certificate authority. So some of you may have heard of Let's Encrypt. 85% of the instances that we were monitoring were using the Let's Encrypt certificate authority. Now you can see over here this massive spike. What happened there is simultaneously a big bunch of instances had their certificate expire at the same time. And all of a sudden, about 100 of them suddenly went offline. Now this was an interesting trait. And what you can see here is over time, as the administrators kind of realize that certificates expired and get it fixed, it goes down. But the problem is, the certificates in Let's Encrypt by default have 3 months expiration dates. So after 3 months, you get this spike up again as people have forgotten to renew again. So these central dependencies in which you're kind of using one certificate authority, again, can result in these servers becoming inaccessible. Now, the next person I want to start picking on is you and me, because the next problem is that users like yourself and I don't help with these problems, because what we tend to do is exhibit very common behavioral traits that, again, push things back towards a centralized model. So again, a simple question. You've joined your instance, you've set up your account, who are you going to follow? Well, what we find is that the top 5% of users are accumulating the vast majority of followers. In other words, you get a few superstars with lots of followers, and then a long tail of very unpopular people. So you might have, for example, our unpopular pigeon, who might only get 10 users, or you might have our incredibly famous and popular grumpy cat, who gets 100,000 users. Now, you might say, well, this is perfectly natural. We all know the power law distribution of social graphs. But the problem is, what happens if Grumpy Cat's server goes offline? If that occurs, because Grumpy Cat is so popular, it's going to have a disproportionate impact on the rest of the network. So even if his server only has himself on, because he is so popular, there's going to be a ripple effect that's going to impact many other users. And this is actually more complicated than it looks. So let's step through an example of what actually happens in practice here. So imagine you've got these 3 networks. You've got OVH, which is a large French web hosting provider. Of course, we've got Amazon's EC2. And then maybe I've got my instance working at Queen Mary University of London. And of course, each one of these servers has its own distinct set of users. Now, again, you say, well, this is actually fairly decentralized, isn't it? Because we've got one server here, only a couple of servers there. They're all disjointed. So that means that even if one goes down, it's not too bad. Perfect. But of course, because we have this remote follow operation, what we might find is that this user on OVH follows this user. And of course, this user is following this one, and so forth. So they've basically created a sort of social graph in which users follow each other. And in practice, what this means is, underneath the bonnet, federated links between these different services being created so that they can pull the content across, such that if, for example, this user posts a comment, it gets pulled across the network to here. So this user and this user are communicating. We can see these links going on. The only problem is, that's not a real social graph. This is a real social graph. It's much more complicated, where you have, for example, very popular users like this one with clearly lots and lots of followers. We have unpopular users like this one. That's just perhaps me with no followers. And then, of course, we have these important nodes. These are what we refer to as bridge nodes, who actually bring together 2 disjointed communities. Now, in this graph, actually, the bridge nodes are the most important. So, for example, what happens if this link breaks because, for example, there's a network partition? Maybe there's some issues In BGP, a router goes down and these networks can no longer communicate. Well, what happens is we then suddenly rewire the entire social graph so that all the content over here is never going to propagate to the users over here because that bridge node no longer connects the two. Now, some of you might be saying, well, I bet in practice that doesn't really happen. I bet in practice most users just stick to their own little community on their own little instance. So the fact that a network partition occurs doesn't really impact in the way that I just said. The problem is you'd be wrong, because actually what we find is that the majority of instances depend heavily on foreign content. So this graph shows the percentage of content being pulled from the remote servers and the home servers. And along the x-axis, we have the servers, individual servers. And what you find is that a small number of servers at this end do actually generate most of their own local content. So these have got a very local, vibrant ecosystem in which a lot of their own content is generated and shared. But in fact, the vast majority of servers rely almost exclusively on pulling content from other servers. So if one of these network partitions happen, these servers essentially die because they don't have a local ecosystem to generate content. They rely on the remote follow operations to pull content from other servers. So we thought this was a really interesting trend because it really brings to the fore the idea of having like a decentralized infrastructure and a social graph laid on top of it, because you create that tension because these two different graphs might not necessarily work in conjunction together. So what we wanted to do was try and actually test how severe this problem is. So with our data, what we tried to start doing is running some simple simulations to test what would happen if certain networks failed or if certain servers failed. So this is just one of the examples that we took from the paper. So what's happening here is along the x-axis, we're removing individual instances. So we're removing servers. And what we're measuring here is the size of the largest connected component in this graph, in this social graph. And what we can see is, as the number of instances removed, the size of the connected component shrinks. And I don't want to go into the technical details if you've not used this vernacular before, but essentially what that means is the connectivity and the ability to spread content depletes rapidly. So for example, removing just the top 1% of accounts decreases this largest connected component to about 25%. So it goes from about 90-something% to 25%. So that means the vast majority of users cannot communicate with each other. Now, if we were to start removing entire networks, so entire autonomous systems, we get even worse results. So for example, if we were to remove those top 5 networks like OVH and EC2 from Amazon, what we find is this social graph just shatters. So everybody breaks off into small communities and people can no longer communicate or share their content. So this is really problematic if, of course, your entire business model is about connecting people and allowing them to interact. So we can also check what actually happens to the content, because that was the social graph. But what actually happens to the hosting of the content? So again, we ran the same experiment. Along the x-axis, you can see what's happening when we're removing ASs. So that's autonomous systems. That's basically a reference to a communication network. And this along the x-axis is removing individual instances. And again, what you can see is as we remove networks and instances from the graph, the amount of content depletes rapidly. And the reason is we have a small number of servers and a small number of networks that are hosting the majority of content. So if they happen to go down, all of a sudden, most of the toots in the system just disappear. So this is the way Mastodon currently works. So one option would be to re-architect this slightly and say, well, what we can actually do is we can replicate the toots. So imagine if I'm following Yanis's server. If I follow Yanis on his server, what could happen is when I pull his toot across to mine, I could actually share it in a peer-to-peer fashion with other people. So I could replicate it. So again, we ran these simulations with this model of allowing me to share other people's toots. And what we find is the results were much more positive. So as you can see here, the amount of toot availability is far better when we're replicating the content than here. But what we still actually see is in the face of a large number of networks going down, you still get a significant portion of content disappearing from the network. And the reason for this is because many of the networks are hosting multiple servers. So for example, what happens if my server is hosted in the same networks as Yanis's? If that happens, it doesn't matter if I replicate his content onto mine. If our network goes down, both of us disappear at the same time. So we don't get perfect replication because we're not being network aware. So we also thought about how we could try to go about fixing this. And what we thought is, well, can we somehow try to detach the connection between our social graph and the underlying infrastructure graph? And we thought the best way to do this would be to simply randomize it. So what we tried doing is whenever you create a toot on your server, what you can do is you can randomly place it on another server. And what we found was that we got much better performance. So this is what happens when you do no replication. So you can see as the servers are being removed, the availability of these toots drops dramatically. This is what happens if we do it with the replication I mentioned before, where you actually, whenever you follow somebody else, you copy their toots to your local server. And again, you can see here that the performance is much, much improved through the replication. This, however, is what happens when we start randomly replicating it. And what we find is that random replicating achieves nearly perfect availability. And the reason is because we do random replication, we never associate a particular toot with somebody's social graph. We put it completely separately on a completely different network. So even if that goes down, it's very unlikely that their random replicated toot would also go down. And even with just 2 or 3 replicas, we can get near perfect availability for a system. So some of you might be thinking that this has been some sort of critique of Mastodon. Now, I want to emphasize at the end that this has not been a critique of Mastodon. I think probably most people on this call, and certainly all the authors of this paper, are actually a big fan of Mastodon. We know it, we love it, and we use it. Now, actually, this made its way into the Mastodon sphere. So somebody who was attending the conference where this was presented actually posted on one of the Mastodon instances about this particular paper. And what we actually found was a relatively negative response from some of the people in the community. So, for example, this one says, all of this scraping of the instances, and they couldn't even be bothered to learn how federation works. Another one was 5 authors, and they didn't even get how it works. Nice. Then we had another charming one. Did they just measure this, or did they just wave their hands around? Now, what we then did is we posted a few replies, and we tried to clarify the intentions behind what we were doing, and we started to get a slightly more sort of positive response, and eventually we even got some compliments, interesting academic paper. And the reason I share these is because I want to emphasize why we're doing this type of work. We don't do it to critique. We do it for the exact opposite reason. We're trying to find some of the trends that get pushed in these new models of decentralization, measure them and understand them, such that when we're designing into the future, we can try to build better systems that better reflect the human trends that we have. Because in many cases, the issues that we're seeing are not fundamental technical problems. They're just problems in the ways that users interact with these systems. And if we can understand the ways users interact with these systems, we can better design them to reflect those constraints and those requirements. So to conclude, when you build a decentralized architecture, in many cases, it does not necessarily equal a decentralized deployment or decentralized usage. And at least in my very humble opinion, we actually need much more measurement-informed development. So when we build and deploy systems, we actually go on to measure, understand how they're used, and then go back to the drawing board to build better systems that better reflect how they're being used in practice. And of course, it's damn hard to decentralize the web. Anyway, thank you very much for listening. Thanks again for the invite from Yanis. And again, if you have any questions, feel free to fire them out now, or alternatively, you can easily Google me and send me an email, happily chat offline as well.
Fantastic. Thank you so much. Everyone can hear me okay now?
Yeah.
Yes, okay. I'm having some audio issues at the beginning of the call. Questions, do not be shy, please hop in. If you don't want to be in the recording, feel free to drop a question in the chat and I will read it on your behalf. Dean, go ahead.
Hey, so you mentioned that a lot of the content that shows up on people's servers comes from foreign servers. Given that that's the case, how common is it that there are really like one or two bridge nodes between a server of like 50 users and the servers with 1 million users?
Well, what you find is that the number of users spread across these instances is sort of power law. So you have major instances like Mastodon Social, in which, you know, literally hundreds of thousands of users congregate. And these obviously generate a large number of content, and this is exactly the stuff that gets pulled and imported into other servers. In many cases, you do find actually individual instances that are bridge nodes on these smaller servers. And one of the reasons is because you actually get many servers which only just have a very, very small number of users on. So in the most extreme case, we find servers that just have one user, and these are specifically set up by people who want to own and operate their own server for their, you know, their own preferences. So it is actually fairly common to have this. I should add though that the sort of availability properties of these larger, well-managed instances are pretty robust. So the chances of bridge nodes on these large instances like Mastodon Social going down are fairly small. And actually what you find, as I said, showed in that box plot, many of the highly unavailable servers that go up and down over time are the ones that are smaller or run by voluntary efforts. And again, I want to emphasize at this point, when I'm talking about unavailability, I'm not doing it in a critical way, because it's also important to recognize that many of these smaller servers are being run on a voluntary no-cost basis. So it's not surprising that some of them go down. And in fact, in some cases, you might find situations where those servers are simply going down because they run out of money. And actually, if it interests you specifically on the bridge nodes, we have some plots in the graphs, plots in the paper that specifically give you the full distribution of those highly central nodes. And if that's not sufficient, we actually have a bunch of graphs looking specifically at centrality metrics I'm happy to share, if you'd like to just drop me an email.
Other questions? Okay, last call before we cut it off here.
I guess I'll ask another one if nobody else is. So I spend a bunch of my time thinking about IPFS these days, and that approach is slightly different in terms of the way in which you find content. In the sense, you use a randomization sort of property to help you find where the content is located, but it stays where it is, right? So it doesn't have that property where you've replicated it to a bunch of random people. There's still a social graph around who has the data, but the finding it mechanism is randomized. How do you feel like that would fit into your modeling?
Yeah, I mean, in my humble opinion, I think it would be a valuable addition to something like Mastodon, because the problem that the Fediverse applications have is that you essentially have two graphs, right? You have an infrastructure graph consisting of nodes connected via networks, and above it you have a social graph. And you often find a tension between these two things, because the social graph is very power law. You have popular users, and that naturally pushes power and responsibility to a small number of nodes in the networks. Now, the model that IPFS follows and other DHTs follow is to actually detach those things. So you actually have a much more uniform spread of responsibility across these different nodes. So in my opinion, actually having a replication model which is underpinned by something like a DHT could be a valuable addition to something like Mastodon. So you still have, of course, the instance model where people join particular instances, but those instances can then federate together using something like a DHT to host and index replicas of the content, such that if one goes down, you can actually fall back onto the DHT and recall the content. And in practice, that might be one of the ways that random replication would be implemented that I mentioned at the end of the presentation.
Anyone else? All right, I'm going to call it there. We can keep it open after the recording for more questions. Thank you so much for that. That was a really great talk. If you're watching on YouTube, please remember to like and subscribe. If a research talk that references a king's head being decentralized from his body doesn't deserve a thumbs up on YouTube, I don't know what does. If you want to suggest a speaker or a topic, there are instructions on how to do that in the description. We'd also love to have you join our research mailing list to receive quarterly newsletters, future talk announcements, and information on research funding opportunities from Protocol Labs. You can do this in the footer at research.protocol.ai. Our next talk is next week, Monday, September 14th at 1800 UTC from Vasilis Kiotis, who is a research engineer in the Resilient Networks Lab here at Protocol Labs. His talk title is Measuring the Performance of Private Cloud WANs. Thanks for joining, everyone, and we will see you.